So in this video, we're going to start chapter number 10, which is Introduction to Organic Chemistry and Hydrocarbon Structure. So in this chapter, we're going to talk about different section. In the first section, we're going to talk about what is organic chemistry and how you define hydrocarbons. Then in the second section, we're going to talk about what are the different types of hydrocarbons. Some of them are alkane and cycloalkane. And in the third section, we're going to try to learn about how to write the condensed and skeletal line structure for those alkane and cycloalkane. And after that, we're going to talk about another type of hydrocarbons, which is alkene and alkyne. And then we move on to another topic called aromatic hydrocarbon. And the last, we're going to talk about how to name any substituted hydrocarbon, how to name them. So let's get started with this chapter, and then let's move on to the next slide. So now let's start with our first section, in which we're going to talk about what is organic chemistry and what are hydrocarbons. So organic chemistry is the study of organic compound and their reaction. So how the organic compound react with each other, that branch of chemistry we call as organic chemistry. Now we're going to learn what is organic compound. So organic compound are carbon and hydrogen containing compound. So those compound that mainly consist of carbon and hydrogen, we call them as organic compound. But sometimes these organic compound also contain, beside carbon and hydrogen, which is the requirement, sometimes they also contain some non-metal in there, like oxygen or halogens, right, along with the carbon and hydrogen. So we're going to talk about all this thing in the next chapter, but right now just focusing on the organic compound, which is carbon and hydrogen containing compound. And the first organic compound that was synthesized, it was synthesized in 1828. And more than 95%, or at least 95% of the non-compound are normally organic in nature. And then rest of the 5% we can have that are inorganic compound, right? And most of the biological compound that we know of or we already knew about are organic in nature. So we're going to talk about this thing in a while. But before that, let's talk about the inorganic compound. What is inorganic compound? So inorganic compound is a small group of compound that contain carbon but not a hydrogen. So this is how you can differentiate between organic compound and inorganic compound. Organic compound is consist of carbon and hydrogen, whereas in organic compound you can have carbon but it's not have any hydrogen in it. For example, if I take an example of carbon dioxide, so this is an inorganic compound. Why? Because it contains carbon but there is no hydrogen attached with the carbon. We have oxygen. So this is inorganic compound. One more example. This is inorganic. One more example is carbon monoxide, CO. Again, same thing. You have carbon but you don't have any hydrogen in this compound, so this is inorganic compound also. So this is how you can differentiate between organic compound and inorganic compound. So in this chapter we're going to talk about mostly of organic compound, which is carbon and hydrogen containing compound, but you should be able to differentiate between the two, organic and inorganic compound. Let's go to the next topic and then talk about what are the common organic compounds that we can use in real life. Okay, so now let's talk about some of the common organic compounds that we normally use in common life. So we can find organic compound in many common products that we use in everyday life. For example, the food we eat contain organic compound. For example, carbohydrate, protein, lipid. They are all organic compound. The fuel we use in everyday life, like propane, gasoline, made up of organic compound. And then some of the consumer product that we use made up of organic compound. For example, plastic, Teflon. So all these are made up of organic compound, and we use these things in our day-to-day life. So by studying the principle and concept of the organic chemistry regarding this, you can learn more about compounds such as these and how they can affect the world around you. So that's why the study of organic compounds are important. So now let's move on to the next slide, and we're gonna talk about now the hydrocarbons, which is a type of organic compound. So now let's start with the topic of hydrocarbons. Let's talk about what are hydrocarbon and what are the different kinds of hydrocarbon we have. So hydrocarbon, as the name is already telling you everything, made up of hydrogen, and carbon is carbon, so that's why the name is carbon and hydrogen. So hydrocarbons are those organic compounds that mainly consist of carbon and hydrogen. And why we make different kinds of hydrocarbon? Because carbon has a special property to make a 4 bond. Why carbon needs to make a 4 bond? Because carbon has 4 valence electron that we already knew about from the previous chapters, and then carbon has to get 4 electron from some other atom to make it octet fully filled, right? So the carbon is going to share the electron with 4 other atom or with the same kind of atom through a covalent bond, right? So basically in hydrocarbon, the other 4 atom can be of hydrogen. Hydrogen is going to share one electron and make a bond, right? Or carbon can make a bond with other carbon. This is also carbon, right? And then we have three more electron in here, right? So that's why, because of this bonding pattern of carbon, where carbon can make a bond with another carbon to fulfill its octets, we can find a different or like vast variety of hydrocarbons, right? Because of this property. So this carbon also can make a bond with another carbon, and then the structure keep on going, right? And then next we're gonna see about, as we know, the carbon is going to make a bond with 4 other atom, or with the carbon, or with hydrogen. So we only talk about the hydrogen bonding and the carbon bonding, but there are some other atom which can bind directly to the carbon atom through a covalent bond, and they are mainly consist of non-metal. For example, nitrogen, oxygen, sulfur, fluorine, and chlorine. So in hydrocarbon, let me tell you one more time, basically contain carbon and hydrogen, but sometimes some other non-metal also be combining with the carbon or a hydrogen to make this hydrocarbon, right? So let's move on to the next slide. Now we're gonna talk about that what are the different ways carbon can bond, right? So we only talk about carbon can make 4 bonds. So remember this thing, you cannot have any carbon without 4 bond in the organic chemistry. So carbon has to have 4 bond, right? So how they can make a 4 bond? There are 3 different ways carbon can make 4 bond to fulfill its octet. First, all the 4 bond are single bond, like we have in this structure. Carbon, all 4 bonds are single bond. And then we can find this kind of structure where carbon make all bonds single bonds. We can find in one of the type of hydrocarbon that we're going to talk about in the next slide is alkane and cycloalkane. This is the type of hydrocarbons where carbon form only single bond, all 4 bond. So what are the second way carbon make a 4 bond? Carbon can make 2 single bond, and then it can make a double bond. So we can find this kind of bonding of carbon where we have at least one double bond and 2 single bond in alkene and aromatic hydrocarbon, which is also a type of hydrocarbons. And the last way that carbon can make a 4 bond is by doing one triple bond and one single bond. So if you can see, we still have 4 bond on carbon, and then we can find this kind of bonding pattern where the carbon make at least one triple bond. This is your triple bond. We can find in one type of hydrocarbon known as alkyne, right? So you have to remember this thing. If we talk about all single bond, alkane and cycloalkane, if we talk about at least one double bond, alkene and aromatic, if the carbon has at least one triple bond, then you can find in alkyne. And then we're gonna talk about now what are alkane, cycloalkane, alkene, aromatic, and alkyne in the next slide. So now let's talk about how we can classify a hydrocarbon. So hydrocarbon can be classified into 4 categories. The first one is known as alkane, second one alkene, alkyne, and then the fourth one is your aromatic hydrocarbon. And this chapter just based on all these 4 kind of classification of the hydrocarbon, and we're going to talk about separately about these classes in this chapter. So what are alkane? If you remember, in alkane, carbon always form single bond. Doesn't matter with its with the carbon or with the hydrogen, you can find only single bond. For example, this carbon is gonna make or is making right now all single bond, 3 with the hydrogen and 1 with the another carbon in there, right? And then again single bond. That's why it's known as alkane. The second one is alkene, and if you remember from the previous slide, we know about the alkene. We should have at least one double bond between carbon and carbon. So you can see over here, these 2 carbon has a double bond between them, and then how many single bond each of the carbon need? 2 single bond to make it 4. So 1, 2, and then 3, 4 from the double bond, right? And then we have an alkyne. Alkyne should have at least one triple bond between carbon and carbon. We can see these 2 carbon has a triple bond between them, and because of the presence of triple bond, how many single bond it need more on each of them? 1, because carbon has to have 4 bond. So 3 comes out between carbon and 1 comes from hydrogen and carbon on either side, right? And then the last we can talk about the aromatic hydrocarbon. So aromatic hydrocarbon is a special type of hydrocarbon where you have alternate double, single, double, single bond, and we're gonna talk about much in detail what are those double bond, and then how you can make these kind of hydrocarbon, what are the properties, right, later in this chapter. But the important thing, you have to know all these classification for hydrocarbons, and we're gonna go individually about all these 4. And then the last important thing that you need to worry about for this organic chemistry part, you cannot form a double bond between carbon and hydrogen. Why you cannot form? Because hydrogen can make only one single bond, because it needs just 2 electrons to complete its octet, and the time it make a double bond is not possible. So from now on, if I say this hydrocarbon has a double bond, triple bond, that means those bonds are present between carbon and carbon, not on carbon and hydrogen. So this is the most important thing, so don't do this mistake. So now let's go to the next slide. So now we're going to talk about what are the properties of the hydrocarbon, whether it's alkane, alkyne, or alkene. So now we know hydrocarbons are non-polar compound because there is no polar bond present in the hydrocarbons, right? And then we know if the compounds are non-polar, we have just one type of intermolecular forces we already know about, which is dispersion forces, because non-polar compound always have dispersion forces, and this is the weakest type of intermolecular forces we already talk about on the previous chapter when we talk about the intermolecular forces. And because of the presence of these dispersion forces in hydrocarbons, the hydrocarbons always have lower melting and boiling point than the polar compound of similar mass, right? If we compare polar and non-polar, non-polar will always have a low melting and boiling point. Similarly, they are immiscible with aqueous solution. Aqueous means water, and we know water is a polar compound, so they cannot mix with each other. So non-polar compound cannot mix with an aqueous solution because of the hydrophobic effect. What is hydro? Hydro means water, and phobic means scare, right? So non-polar cannot mix with polar solution. So now let's go to the next slide, and so now let's try to do a problem based on the concept of organic and inorganic compound and classify all these compounds that is listed on the bottom, whether they belongs to organic or inorganic compound, or whether they are hydrocarbon or not, right? So let's start with the first one, which is C6H12O6. This is an organic compound. Why? It is made up of carbon and hydrogen, and then we know most of the hydrocarbons are present made up of carbon and hydrogen, but sometimes some other non-metal also can be attached with these carbon and hydrogen. So this is an organic compound, right? And this is also an hydrocarbon. NaCl, this is an inorganic compound. It doesn't have any carbon and hydrogen. What about the third one, hydrochloric acid? This is also an inorganic compound. It doesn't have carbon and hydrogen, so it doesn't belong to an organic compound. The fourth one, C3H8, the time-IC is made up of carbon and hydrogen, organic compound, right? And we can classify as hydrocarbons. The fifth one, also an organic compound. Why? Because it's made up of carbon and hydrogen, and sometimes some non-metal also get attached, right? But basically it has carbon and hydrogen, organic compound. Water, which is H2O, it has hydrogen but it doesn't have carbon, so this is inorganic compound. Then we have fat. Fat is an organic compound. We already talked about in the beginning of this chapter. Then we have carbon dioxide. We know we have a carbon, but we don't have any hydrogen in there, so this is an inorganic compound. So make sure you know how to differentiate between organic and inorganic compound, right? So that's why we did this problem. So now let's go to the next slide, and then we're gonna start with a new section called alkane and cycloalkane. And we already know alkane and cycloalkane is a type of hydrocarbons, right? One of the classification. So we already know alkane and cycloalkane. Was the special characteristic in alkane and cycloalkane? The carbon bond contain single bond always, or carbon hydrogen bond. So that means carbon can form only a single bond, not a double bond, not a single bond. That's how we can classify all the hydrocarbon as alkane and cycloalkane, right? So carbon single, carbon hydrogen single bond only. And then how you're going to write the molecular formula? This is the formula that we're going to use to write the molecular formula. And what is molecular formula? Molecular formula is how many atoms are present to make that hydrocarbon in how many quantity. Means if you have carbon and hydrogen, how many carbon is present, how many hydrogen is present. So we define through a molecular formula, right? And then the formula says CnH2n plus 2. N is the number of carbon atom in that formula, right? And then if you have certain number of carbon, how many hydrogen you have to get that formula, right? So let's take an example on this right now. So if I have C1, if I say n equal to 1 with this formula, how many hydrogen this compound should have with one carbon? So n is 1, right? So 2 times 1 is 2, add 2 to it, 4. So the formula is CH4. We usually don't show 1. So if you have one carbon, you have to have 4 carbon attached to that carbon to make that hydrocarbon as an alkane. For example, if I have 5 carbon, how many hydrogen I have to have so that we can say this hydrocarbon is an alkane? So again use the formula CnH2n plus 2. The time I see 5, I know n equal to 5. 2 times 5, 10. Add 2 to it, 12. So we have to have 12 hydrogen with 5 carbon to make that thing as alkane. So this is how you normally do it. And we have a special name for those hydrocarbon where we have all bonds, where all bonds are single. We call those kind of hydrocarbon as a saturated hydrocarbon. Saturated means all the carbon have all single bonds, right? Or you can say the maximum number of hydrogen atom per carbon atom, right? So let's take an example for methane. We already done the methane example over here. If you have 1 carbon, you have to have 4 hydrogen. Let's talk about the second type of alkane, ethane. How many carbon you have in this ethane molecular formula? 2 carbon. How would I know it need to have 6 carbon? By using the formula CnH2n plus 2. 2 times 2, 4, plus 2, 6. That's why the formula is C2H6. For propane, C3, how many hydrogen? 3 times 2, 6, plus 2, 8. So C3H8. So this is how you can figure it out, the molecular formula for any alkane using the formula, right? So let's go to the next slide and then see some of the structure. So these are the simplest alkane structure. So these are called a Lewis structure, right, where you can see all the bond and all the atom in that particular compound. So in the first one, which is methane, you can see the carbon and all single bond along with the hydrogen, right? We call this as a Lewis structure, like I said, or you can say expanded structure. Expanded structure means you are showing each and every bond in that particular compound, right? You have to show the bonds. For example, the second one, which is an ethane, which is C2H6. So how many carbon? 2 carbon. So how you make it? Put 2 carbon, make a bond connecting 2 carbon, and now you have 6 hydrogen, and then each carbon have to have 4 bond. So put 1 hydrogen on each, 3 hydrogen on the other one. So that means each carbon has 4 single bonded carbon atom to complete its octet. So that's why the structure, Lewis structure, is like this. Similarly for C3H8, we have 3 carbon, and then on the corner carbon you have 3 hydrogen, and the center carbon has 2 hydrogen, because the other 2 bonds are connected through a carbon-carbon to make it 4 for this carbon atom, right? And then the second type of structure that you seeing over here, this is we call as space filled model, where you normally see a 3D structure of that particular compound, right? So this is a 3D shape of the compound for methane, for ethane, and for propane, right? And if we talk about what's the shape of each individual carbon over here, if we talk about for methane, what's the shape of this methane molecule? Can I say the shape is a tetrahedral? Because if you remember from the previous chapter, you have 1 carbon, 1 atom in the center, 4 atoms surrounding it. The shape will be a tetrahedral shape, right? So if you can see on the bottom, this represents a tetrahedral shape, right? The space filled model. Similarly, both the carbon in the second structure, both of them has a tetrahedral structure. Same thing for the third compound, all the 3 carbon atom has a tetrahedral shape. That's why you will see a something bent like structure over here. So make sure you also know about this shape around the carbon atom in the organic compound in alkane. So now let's talk about a special property of an alkane called conformation, right? So what is conformation? So if you can see, let's take an example over here for one alkane molecule where you have carbon, 5 carbon, and like we have different hydrogen connected to all the 5 carbon, and all of them are single bonded, so they are alkane. So what's the special property of this alkane molecule? That we have a single bond between carbon and carbon, and this single bond between carbon and carbon, you can rotate this single bond. If you hold this one carbon and then rotate the second carbon around this carbon, you can make a new shape of the molecule because of the rotation of this single bond between the two carbon. And then the new shape that you're going to make, we call that new shape of alkane as conformation, right? So conformation is the many possible rotational form of a molecule. Why? Because we have a single bond that you can use to rotate a molecule. For example, take this an example. So this is carbon, right? And if I use this bond, and then if I hold this carbon steady and I rotate this carbon along this bond, you're gonna get this structure, right? So these are the same molecule, but they are different because of their rotational shape, because they have different shape because of the rotation of the single bond, right? So for example, let's take one more example. If you have this carbon, you have a hydrogen, so let's take this example with where you have 3 carbon. If I use this single bond to rotate this molecule, for example, if I rotate this single bond, then we can make a new compound which is something like this, H, then you have carbon, hydrogen, and then you can have carbon over here. So even though this is the same molecule, both of them, but because of the rotation of around this 2 carbon, because of the single bond, we can have a new shape, right, of the same molecule. And we call these 2 molecules that we just got as a conformers between each other, or you can say for each other, right? So what's happening over here, if we see clearly, if I start from this carbon and if I follow the bond between carbon and carbon, let's start with this. If I follow this bond, I end up with the 3rd carbon, right? I haven't missed any carbon. We had 3 carbon, we start with the one corner carbon, end up with the last corner carbon, and we include every carbon. Let's see if we have the same thing over here. So if I start with the same carbon, which is a corner carbon, if I follow this carbon bond, so without breaking in my line, I'm touching each and every carbon that we have in this compound. So that means these 2 compounds are same compound, but the shapes are different because of the rotation of the molecule. So we can say these 2 molecules are conformation or conformer, you can say conformer of each other, right? So these are not a different molecule. This is the important thing. So let's take a couple of examples on the next slide and try to understand more about this conformation. So let's take this example. We have this organic compound which is an alkane. How many carbon we have in this molecule? I have 1 2 3 4 5. We have 5 carbon in there, and then see we can make these different compound just by rotating a carbon single bond. So depending on which carbon single bond we are rotating, we can make all these molecules. So let's start with this one, the first one. So if you can see, We start with 1, 2, 3, 4. Now the fourth and fifth single bond we rotated, so that means I rotated this bond, right? And by rotation this carbon goes up and then make this kind of shape, right? And then what's the requirement before you can say these two molecules have the same compound? So you have to start with one of the corner carbon and you have to go all the way till the last carbon without breaking the bond, right? Or without breaking this line. If you're touching all the carbon that you touched in the first structure, that means both the structure that you made are conformers of each other. If not, then they are a different structure, right? So in the first one I touch everything. Let's go to this molecule now. I start with this corner carbon because we don't have any carbon before this, right? Let's start with this. Let's follow the carbons. Did the line miss any of the carbon in this structure? No. If I follow all the carbon-carbon bond, I touch each and every carbon, right? So that means both these structure are conformers. They are just different just because of the shape. Let's try the third one again. Let's start with the corner carbon and follow this carbon-carbon bond. So I'm again touching all the 5 carbons. So this means this new shape of the compound is because of the rotation between 1, 2, 3, 4 between carbon number 3 and 4 single bond. I rotated this molecule, right? Same thing with this compound on the bottom left. If I start with this corner carbon, let's follow this carbon, the bond, right? So I'm touching each and every all the 5 carbon without breaking up the line that we are following through a bond. That means this is also the same kind of compound, but they have a different shape, right? Same thing over here. Start with this, follow the carbons. I haven't missed any carbon conformers. Again, let's start with this corner carbon. Let's follow the bond. I touch all the 5 carbon. That means it's a same molecule, different shape. Let's start with the corner carbon. 1, 2, 3, 4, 5. Again, same molecule but a different shape, conformers. So all these 6 structure that you're seeing over here are the same molecule but a different structure or different shape of the molecule because of the rotation of single bond between the carbon. So this is how you can verify whether the molecules are conformers or not, right? So now let's try to do this problem based on the concept that we just learned about the conformation. So the problem is saying the structure is given of any molecule that has 4 carbon number 1, 2, 3, 4, and it's saying which of the lower loose structure out of the 5 loose structure that is given, which are equivalent to the loose structure in the box. So which molecule is same like the one that is given in the box, right? So to make the same molecule, you have to have the same number of carbon atom in the molecule in the structure given below. So we started with 4 carbon in our compound. So let's see how many of these loose structure has 4 carbon in there. The first one has 1, 2, 3, 4, 5. It's not possible to have the same loose structure because it has 1 more carbon. Let's talk about the B. 1, 2, 3. It's also not possible. It has only 3, not 4. So you cannot make the same kind of loose structure, right? Because we had 4 structure in our 4 carbon in our given structure. What about the C? 1, 2, 3, 4. It's possible. We can check later on. What about the 1, 2, 3, 4? It's also possible. And the E one is 1, 2, 3, 4, 5. You have 5 carbon in there. It's not possible. So we have to figure it out between C and D. which one has the same structure or same loose structure like the one we have on the box, right? So how are we gonna determine? So in the given structure, if we start with this corner carbon atom, if I follow the carbon-carbon bond, I am touching all the 4 bonds without breaking up the line. So we have to apply the same rule. See if we can touch all the 4 carbon atom. If I start from the one side to the another side, that means it has the same structure or just the same loose structure or same molecule, right? So let's start with C. This is a corner carbon. We can start from this side and let's follow the carbon-carbon bond. So I can touch all the 4 carbons. So this molecule can have the same kind of loose structure, the one that is given, right? Let's talk about the D. If start from here, 1, 2, 3, 4. So this is also possible, right? So we can say out of the 5, these option number C and option number D have the same loose structure like the one that is given in the box. And we can also say these two are conformers. A and D, the structure and the D are conformers, and then structures C and D, they are also conformers, right? That means they are conformation for each other, right? So they are the same molecule, but because of the rotation around the single bond, they have a different shape. So let's take a couple of more examples based on the concept of conformation and then try to learn the concept a little bit more, right? So let's take an example. I have CH, this molecule that I'm drawing, H. And then let's make one more. So now let's try to solve this problem. So the structure is given in the given structure, which is in red color. How many carbon atom you have in there? We have 1, 2, 3, 4, 5. So this is the structure that is given. You have to figure it out of the two structure that is given in the green color, which one is a same structure like the one we did in the red color, and which one is not the same structure. Basically, which one out of the two, which one is a conformer of the given structure which is given in red. So how are we going to figure it out? So we have to apply the same thing, figure it out how many carbon atom you have in the given structure. We have 5. Let's see if each of the two compound have 5 carbon. If yes, then both might have the equal chance to become a conformation of the given structure. So in the first one we have 1, 2, 3, 4, 5. So it's possible to have the conformation. Second one, 1, 2, 3, 4, and the 5. We have 5 carbon in both of them. Now you have to apply the second trick, where we normally do it when we start from the one of the corner carbon atom, basically the first carbon, and if you follow the carbon-carbon bond, I am touching all the 5 carbon starting from till the end. So if I can do the same thing in any of the two structure that is given on the bottom, that means that structure is same like we had in the red color. So let's start the same concept over here. Let's start with the first carbon and follow the bond, carbon, carbon, all the carbon. So that means I can touch all the 5 compound or carbon in this molecule. So this means these two are same compound, but they have a different shape because the molecule rotated about carbon 3 and carbon 4, and that's why these two become or just place at the bottom, right? Because you rotated the compound. Let's talk about the C, the second one. Start with the first one and let's connect all the carbon if you can connect. Start with here 1 2 3. Now I have to make a choice. Either I can go up or either can go straight. There is no way I can connect all the 5 carbon without breaking up the line, right? So if I go up, so I'm making this line, so I'm connecting all 4. I'm not using this in our counting, right? If I would have gone straight, that means I'm not connecting this 5th carbon. So that means these two compound are not same compound. They are not conformation of each other or conformer of each other, because I cannot join all the 5 carbon in a single line if I follow the bond, carbon carbon bond. So this is how you can differentiate between the conformers or if there is something else in the given molecule, right, in the option given below. So this is how you can identify. So make sure you learn this concept. This will be helpful for you to figure it out, different kind of compound. So now we're gonna learn about a special type of term called isomer. And then once we learn about the isomer, then we're gonna talk about what are structural isomer. So now let's talk about the first. What are isomer first? So isomers are the compound or the molecules that have the same molecular formula. You can say same molecular formula but different arrangement of atom, right? Different arrangement of atoms, how the atoms are arranged within that molecule, right? So we call those kind of molecules are isomers, right? And then there's one type of isomers we call as structural isomer that we're going to talk about especially in this topic for alkane. So what are structural isomer? Structural isomer means different compound with same molecular formula, right, but different atom connectivity. So in this case the atoms are connected differently. So we're going to talk about and see several examples of structural isomers. Then we have constitutional isomer. Constitutional isomer is the same name for or the synonym name for the structural isomer. So if I say constitutional isomer or a structural isomer, we means same thing, right? And then a structural isomer have different physical and chemical property because both the structure are different, right? So let's talk about these structural isomers in the next slide, right? We'll take an example. So let's take an example of butane C4H10. I can make C4H10 like this, where we have 4 carbon connected in a straight line and then we have hydrogen connected on each of them, right? There is one way of writing the loose structure for C4H10. There is another way. I can draw the same molecule but with a different connectivity of carbon atom. If you see this structure, how many carbon atom we have in there? 1 2 3 4, exactly 4 carbon atom. How many hydrogen? 10 hydrogen, same number of hydrogen. How many carbon in the first one? 4 carbon, 10 hydrogen. So that means both of these structure have the same molecular formula C4H10, but the order of connectivity of carbon are different. So what you're seeing over here, we have 4 carbon in a straight line, but over here we have 3 carbon in the straight line. That means one of the carbon we break the bond, right? For example, this bond, and then we move this carbon on the third carbon, right? And then remove this hydrogen and put it on the third carbon over here. So what happened over here? We break the bond to make this a structure, right? That means we have a different connectivity. So this carbon was connected to the third carbon in the previous picture, right? But in this case, this carbon connected to the second carbon now. So that means we break the bond, put it, make up the new bond with a different carbon. So that means they are structural isomer. They are different structurally, right? So that's why we call them as structural isomer, same molecular formula but different connectivity of carbon atom in this case. So now let me ask you a question. Are they conformers? Conformers? No, they are not conformers. Why? Because if you start from one of the carbon atom, we connected all four in a straight line, but we start with the same carbon atom in a different structure. If I go all the way straight, I am not connecting this carbon atom which is on the 4. So that means they are not having the same shape, right? So that means they are not conformers. So this is how you can apply the conformers concept to verify whether they are conformer or not. If they're not conformer, in this case they are structural isomers, right? So let's try to take out this concept and then try to do one problem on the next slide, right, to figure it out which one is your structural isomer. So the problem is saying determine which pairs are structural isomer. Means you have 3 options, and in each option you have a pair of structure, and you have to figure it out which pair of structure represent an structural isomer. So we only talk about what a structural isomer means. Same molecular formula but different connectivity of atom. Connectivity of atoms. So let's follow the same concept. How many carbon you have in the first option A in both of them? 1 2 3 4 1 2 3 4. What's the molecular formula? C4. If you have 4 carbon and all of them are connected single bondly with the hydrogen and carbon, how many hydrogen you have to have? You have to follow the same formula, CnH2n plus 2. So that means I can have 10 hydrogen, and if you count 1 2 3 4 5 6 7 8 9 10, 1 2 3 4 5 6 7 8 9 10. So that means both of them has same molecular formula. Let's see if the atoms are connected differently. So we start with over here. If we can connect all 4, yes, we can connect all 4. Let's start with again over here. Can I connect all 4? 1 2 3 4. I can connect all 4. So that means they look different in shape, but the connectivity of atoms are same. It's not different. So this is not a structural isomer pair. Let's talk about the second one. How many carbon? 1 2 3 4 5. 1 2 3 4 5 6. We have 6 in there, so they cannot have the same molecular formula. Why? Because if you have 6 carbon in here, you should have 14 carbon. For this one you have 5 carbon, then you should have 12 hydrogen. So they have different molecular formula, so they cannot be a structural isomer. The first condition didn't work. What about the C? How many carbon? 1 2 3 4 5 6. It has a formula of C6H14. How many on this? 1 2 3 4 5 6. Formula is C6H14. So they have same molecular formula, but let's say if the arrangement of the atom or the connectivity of the atoms are different or same. Let's start with one of the carbon which is on the corner, the side one. Let's connect all the carbon. 1 2 3. Now I have a choice. I can go up or I can keep going straight. Let's keep going straight. So the maximum carbon that you can connect, if you go from one end to the second end, other end, 5 carbon, right? I cannot connect this carbon. Let's do if we can do the same thing or not. If I have 1 2, if I start from here 1 2 3, 4, 5. So I can connect all the 5, but I can connect this one, right? So this means the connectivity are same, but the thing is that the sixth carbon that we have is connected on the third carbon in the first structure and on the second carbon on the second structure. That means the connectivity of this carbon is different in both the structure, right? So that means the bond connectivity are different, but they have the same molecular formula. They are structural isomers. So this is the right one. C is your correct answer. Right. So this is how you can verify whether which carbon atom are connected differently in both the structure, even though the first one they have to have the same molecular formula. So make sure you apply the concept of this and then figure it out which one is a structural and isomer. Right. Now let's talk about the physical property of the structural isomer. The time I see a structural isomer, we know they have a different structure, right? So let's take an example. You have 5 carbon, molecular formula is C5H12. How many carbon there? 1, 2, 3, 4, 5. C5H12. How many in there? 1, 2, 3, 4. 1, 2, 3, 4, 5. Same number of carbon, C5H12. So in this, if I start from here, I connected all the 5. If I start from this corner, I connected 4, but the 5th one is connected on the second carbon. So that means they have a different connectivity. So they are structural isomer of each other because they have the same molecular formula. What about this last one? If I start from this one, I connected 3, but what I'm seeing over here in the previous example, we had just 1 connected carbon on the second one, but over here we have 2 connected carbon on the second one. So that means they have a different connectivity in all the 5 carbon, right? They are connected differently. They have a different structure. So all 3 are structural isomer of each other because all of them have same molecular formula, but they have a different connectivity of carbon in their structure, right? So now let's see what are the physical property of these structural formula. Because of the different structure, they might have a different dispersion forces between them, and because if they have a different dispersion forces, they might have different boiling and melting point. So how would the dispersion forces affect the boiling and melting point? We already know about this thing from the previous chapter, that if you have dispersion forces depend on the surface area. If the 2 molecule is contacted with a greater surface area, that means they can have strong dispersion forces, right? And then the concept is, if you branch the structure, if you put more branching, means in this structure, this is a straight line structure. Here I branch one thing, I put one thing on the top of the straight line, I branch one. Over here I have 2 branching on the straight line, right? So higher the number of branching on the molecule, you will always have the less surface area, right? And if you have a less surface area, you will have a less dispersion forces. If you have less dispersion forces, that means you will have lower melting and boiling point compared to the same structure that is not branched. For example, let's take this example. There are structural isomers, same molecular formula. The boiling point of the straight line structure structural isomer is 35 degrees Celsius. But if you branch one time, then the boiling point get lower. If you branch one more time on the same structure, if I put one more carbon on the second one, you branch more. That means your boiling point also decrease a little bit more because of the less surface area. So you have to remember this concept too. So now we're gonna learn about how to name and write the name of the alkane or draw the structure of an alkane, right? So now let's get to the next slide. Then we're gonna see a table that will help you to better understand how we normally name and draw the alkane molecule. So let's go to the next slide. So if you can see on this slide, this will help you to understand how we name an alkane molecule and how we draw it. So it depends on the number of carbon atom that you have in that alkane molecule that we use to name an alkane. So depending on how many carbon, if you have 1, 2, 3, 4, 5, keep going on until 10. So these are consist of how many carbon atom you have in your alkane molecule. And then we have a special name we call as IUPAC name, IUPAC name. So this is a scientific name that everyone use in the scientific world. So you have to use this word, and this IUPAC name is based on some rules that you need to know, and you have to follow all the rules before you can name any hydrocarbon molecule, right? And then the last one is showing you the molecular formula, and we already know the formula CnH2n plus 2, right? So depending on the number of carbon, we have a special prefix we call as, like in this case, if you have a 1 carbon alkane, if you have 1 carbon, how many hydrogen you have to have? 4, based on the formula CH4, right? So if you have 1 carbon, your name will be meth. If your compound contain 2 carbon, eth, right? If the carbon is 3, prop, 4, but, 5, pent, 6 is hex, and keep going on, hept, octane, oct, non, dec, right? So depending on the carbon. And then if you're naming the compound as alkane, the ending word will always be ane, right? For example, if this is an alkane compound containing 1 carbon atom, then meth, put an and word, ane, methane. If the alkane compound has 2 carbon, how you name it? Ethane. If 3 is your prop, propane, right? 4 is your but, butane. 5 is pent, right? 5 is a pent, and this is an alkane, pentane. Then we have hexane, hexane, heptane, heptane, right? Octane, nonane, decane, right? And based on which type of hydrocarbon we are focusing on, the ending word will change. We're gonna talk about this concept in a while, but right now just remember that it should end with A and E, right? And we already talk about how you can make a molecular formula if I know the number of carbon that compound has, right, with the formula if it's an alkane. So let's take a couple of more examples to figure out this concept and apply the same concept to write the name of the molecule. So what's the name of the compound with this Lewis structure? So if the Lewis structure is given, how are you going to name this compound? The first thing that you need to know, figure it out whether it's an alkane or not. As we can see the structure, all the bonds with the carbon are single bond. So the time I see single bond, I know this is an alkane molecule, right? And now we figured out it's an alkane. Whatever the name we're going to write for this compound should end with A and E, right? Then we have to calculate how many carbon we have in there. Start from one corner, 2, 3, 4, 5, 6, 7. I have 7 carbon. What's the molecular formula? If I have 7 carbon, how many hydrogen? 16 from the formula CnH2n plus 2. And the time I see I have 7 carbon, what's the name of 7 carbon? Hept. So it's heptane. So the name is heptane. So this is how you normally name any alkane. Let's take one more example on the same slide. If I have C, what's the name of this organic compound? The first thing that you need to figure out, all of them are single bond. This is an alkane. I need to write the name according to the alkane. And then second, count how many carbon atom? 3. If you have 3 carbon atom, how many hydrogen you have to have? 8, and you can count it from here too. And then if it's an alkane, the ending word will be ane, but see how many carbon atom? 3 is prop, and then ending word will be ane, propane, because 3 carbon is prop from the previous slide. So this is how you can name any alkane molecule, right? Or you can write the molecular formula for any alkane molecule too. So now we're gonna learn about how we can write and name an cycloalkane. As the name is already saying it, this is an alkane. Now we're gonna figure it out what is meant by cyclo, right? So for example, let's take an example. If I have 3 carbon, right, this is CH, CH, H. What's the name of this alkane? I have 3 carbon, all are single bonded, so that means the name is propane of this compound. And so this compound has 2 free end, right? So this carbon doesn't have any carbon after this, so this is one end, this is second end, and this is a carbon atom at the center, right? So is it possible if I can use all the 3 carbon and more than 3 carbon for rest of the other alkane molecule and can join this carbon with this carbon? Can I join this thing? Yes. If I join these 3 carbon, we're gonna make something like this structure, right? If I hold this carbon and join with it, and now how many hydrogen atom you have in each of them? 2 hydrogen. This carbon need 2 hydrogen, this carbon need 2 hydrogen to make it 4. So now each carbon has 4 bond, right? All the 3. And then let's try to make the molecular formula for this cyclic ring structure. So what you have over here is like a ring, all the ends are closed, right? There is no free end, and this kind of structure we known as cyclo. This is like a cyclic compound with a no free end. So let's try to write the molecular formula for this cyclic ring structure containing 3 carbon. So how many carbon you have in here? 3. How many hydrogen in this one? 1, 2, 3, 4, 5, 6, right? 3 carbon, 6 hydrogen for this cyclic. What's the molecular formula for the non-cyclic compound containing 3 carbon? 1, 2, 3, C3. How many hydrogen? 1, 2, 3, 4, 5, 6, 7, 8. So if we can compare the two structure, one in a straight line with 2 separate ending, one in a cyclic compound, what's the difference you seeing in the molecular formula? Here you have how many hydrogen connected with the 3? 8. Here we have 6. So what we're seeing over here, whenever you make a cyclic compound, we always have 2 less hydrogen with the same number of carbon. So that's why we're gonna use a different rule called CnH2n for a cycloalkane, right? So you have to remember this concept, that the name is saying cycloalkane. Why this is a cycloalkane? Because each and every bond are single bond, and then this is a cyclic compound, that's why cycloalkane. And the formula that we're gonna use is CnH2n to figure out how many carbon and how many hydrogen connected to that carbon in a cycloalkane. And again, all carbon atom in a cycloalkane are also tetrahedral. Why? Because each carbon is connected to 4 other atoms, so that's why it's a tetrahedral. One more time, right? So let's take one more example, pentane, that is given on the slide. You have 5 carbon in here, and if I use this carbon and this carbon, and if I going to attach these 2 carbon together, so they're gonna make a bond, and now you have to remove these 2 hydrogen, or else carbon will have 5 bond. So now they're gonna make a cyclic compound, right? 5 carbon, how many hydrogen in there? 10 hydrogen now, right? So that's why the formula is CnH2n. you will always have 2 less hydrogen in a cyclo compound compared to non-cyclic compound. Now let's try to see how we normally name any cycloalkane compound. So depending on how many carbon atom is present in that ring type of structure, we name a cyclic compound accordingly. If you have 3 carbon atom in a ring, that means 3 carbon is what? Prop. If you remember, this is an alkane. If you remember, if you see over here, everything is single bonded propane, but they are in a ring like structure. So whenever you have any alkane in a ring like structure, you start your name with a cyclo. Cyclo represent that we know this is a ring structure, cyclopropane. What about if you have a ring of 4 carbon atom? 4 carbon atom is bute. This is an alkane, butane, but is a cyclic compound, cyclobutane. Similarly, we have cyclopentane. You have 5 carbon in a ring. 6 carbon in a ring is hexane, cyclohexane. Same thing, cyclopentane, cyclooctane. So don't forget to write a cyclo in the front of the any alkane molecule, because if you forget to write any cyclo, that means we are talking about a straight chain alkane, not a cyclic ring structure alkane, right? They have 2 different meanings. So make sure to always write a cyclo for a cyclic ring structure. So let's try to do this problem over here. What is the molecular formula for a cyclooctane? The time I see a cyclo written over here, I know the formula that we're going to use is CnH2n. The time I see cyclooctane, oct mean 8 carbon atom. How many hydrogen? 2 times 8, 16. C8H16. How the molecular formula different from the molecular formula of just octane? So in this case, there is no cyclo. So this is a simple alkane. So the formula will be CnH2n plus 2. So octane is 8. 2 times 8, 16 plus 2, 18. So this is why you have this formula C8H18. So this is how you can make a molecular formula based on whether the compound is cyclo or a non-cyclo. Right. Okay, so now let's talk about how we can write the organic compound in a different way. So till now we just learned about how to draw the structure in a Lewis form, but sometimes the organic compound is so big in size, then to write the Lewis structure is sometimes very difficult to show all the bond, right? So that's how we're gonna use a different way of writing an organic compound, which we call as a condensed way of writing or a skeleton line structure, right? So and we're gonna learn about these 2 way of writing the organic compound beside the Lewis structure that we already learned. So condensed structure and skeleton line structure both have the shorthand notation way of writing. So let's talk about the condensed structure. So condensed structure show all the atom but omit most of the bond. So in condensed structure, you just show the atoms, but you don't show the bond in them. In the second one is skeleton line structure. It show all the bonds, but it doesn't show any of the atom. So that's the difference between condensed and a skeleton. Condensed, no bond. Skeleton, no atom you are going to show, right? So let's go to the another slide and we'll try to learn about writing both the structure, right? So let's start writing and try to get some idea about writing the condensed structure of the organic compound. So how you could write a condensed structure? Let's take an example of the Lewis structure that we have been learning since the beginning of this chapter, right? We have this carbon. How many carbon we have there? 1, 2, 3, 4, 5 carbon, and we have like 12 hydrogen on there, and we can see each and every bond, right, between carbon and carbon, between carbon and hydrogen. So this is a Lewis structure way of writing. But to write a condensed form, we usually don't show a bond, so and we just show the atoms. So let's start with this carbon. If I write this carbon, how many hydrogen attached to this carbon? 3 hydrogen. If you can see 1, 2, 3. Now let's go to the second carbon. How many hydrogen atom connected to the second carbon? 2. 1, 2. CH2. What about the third one? 2. CH2. Fourth one, 2. Fifth one, 1, 2, 3. CH3. So this is how you write a condensed structure. You have to show only the atoms. How many hydrogen or other atom connected to the carbon. So this is how you write it down. CH3, CH2, 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 CH3. So by looking at condensed form, I know on the first carbon we have 3 hydrogen. Second carbon I have 2, and same thing goes on. Right? There's another way of writing the condensed structure, because sometimes you have to write CH2, CH2, CH2 multiple times. So we can just abbreviate this CH2. So let's say how many CH2 you have in this entire molecule. I have 1 CH2, 2, 3. Can I write this structure something like this? CH3, CH2 parenthesis 3 times and then CH3. So this parenthesis is telling you that we are repeating this CH2 unit multiple times, right? In this case 3 times. So instead of writing again CH2, 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 I am just writing 1 time CH2 and putting a parenthesis with 3, so that we know that we are repeating this CH2 3 times in this structure, condensed structure. So this is how you normally write the condensed structure. Let's go to the next slide and try some more problem based on this concept. Now let's try to do this problem over here. Write the loose structure for CH3, CH2, CH times 6 CH3. What is the name of this straight chain alkane? Right. The time I see this condensed structure formula, because I cannot see the bond in there, so that means this is a condensed structure formula. This is a condensed formula, and I have to make, using this condensed formula, I have to make a loose structure. So let's try to do this problem. The time I see CH3, CH2 parenthesis 6, I know this CH2 is repeating 6 times, right? So I can say something like this: CH3, CH2, 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 and then CH3. So 1, 2, 3, 4, 5, 6. Yes, so this is the condensed formula. And then can I make a loose structure from this condensed formula? Yes. So let's start with this. The first carbon has how many hydrogen attached to it? 3. So carbon, 3 hydrogen with a bond. Second carbon has 2 hydrogen. Second carbon, 2 hydrogen. And then same thing, third, fourth, fifth, sixth, right? And the last one has 3 hydrogen. So the best way how you can draw a loose structure, I would recommend make the number of carbon, how many carbon you have in this structure. In this case we have 8 total number of carbon. So put 8 carbon, 1, 2, 3, 4, 5, 6, 7, 8, and make a single bond between them, right? And then just put all the rest of the hydrogen that we have over here. Hydrogen, so this is how you can make a loose structure, right? If I say what's the molecular formula for this structure, how are you going to write the molecular formula? So you have to count how many carbon atom you have in there. You have 1 carbon atom in here. You have 6 carbon atom because you have the parenthesis 6 outside. So 6 plus 1, 7, and then you have 1 carbon at the end, 8. So C8, how many hydrogen? 3 from here, 3 from here, 6, and then 2 times 6, 12. 12 plus 6, 18. So this is the molecular formula, or we can also confirm by the formula CnH2n plus 2. You have 8 carbon, 8 times 2, 16 plus 18. This also confirm you have the right molecular formula. So you can convert one form into another form, from molecular formula to the condensed formula to the loose structure, or vice versa. So now we're gonna learn about how to write the condensed structure for the branch chain alkane. If you remember from the structural isomer, we have the branch chain, right? What is branching mean? Let's say if you have these 3 carbon and then you have hydrogen, 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 then you have one more hydrogen, and if you have carbon over here with the hydrogen. So if I start from one end and if I go across without breaking a bond, if I go on the second carbon, now I have a choice to go up or straight. If I choose to go straight, then I'm not including this carbon in our line, so this is a branch that we didn't include in the straight line that we just drew. Second, if we would have gone like this 1 2, if I would have gone up, then this carbon will be treated as a branch carbon. So you can say branch carbon are that carbon that it doesn't include in a counting whenever we count a number of carbon atom, right? So now we're going to learn about how to write the condensed structure for these kind of branching, right, in an alkane. So let's go to the next slide and try to learn about the same concept in a detail. So let's take this example. You have this loose structure of 2-methylbutane, but we haven't learned about how to name it, so we are not concerned about right now what's the naming. But let's go to the loose structure. How many carbon? Let's start from here. If I go straight, I can go up or I can keep going straight. Let's keep going straight. So this carbon is not the part of this straight line that I used without breaking up the line. So this is a branch carbon. This is a branching, right? And now we have to use a condensed structure for this branching structure. So let's do the same thing. The first carbon has 3 hydrogen, 1 2 3. Second carbon has 1 hydrogen. You write hydrogen over here and then put a bond and put CS3 on this carbon. How many hydrogen? 1 2 3, right? So you're showing the bond in the condensed structure just to show everyone else that this carbon is a branch carbon, right? And then keep going on for the rest of the CS2, CS3, right? But if you don't want to show the bond, there is another way of writing the condensed structure which can show you the branch carbon too. So you write CS3, same thing, CH, and you have to just write the branch carbon with a parenthesis, right? So this parenthesis will tell that this carbon is a branch carbon. How would I know this is a branch carbon? So the time you write CS3, CH, CS3 with a parenthesis, CS2, CS3, the time you see over here, this carbon doesn't have 4 bond in there. If this CS3 wouldn't be a branch, let's assume if this CS3 wouldn't be a branch, then this carbon cannot have a 3 hydrogen atom because the center carbon cannot have 3 hydrogen, right? The time you're writing 3 hydrogen, we know that this is not the part of this straight line chain. This is a part of a branch, right? So this is how you normally write the branching carbon in the form where you show the bond, or in the form of the parenthesis where you show the branch carbon along with the same line, right? Let's take one more example of the loose structure. So this is the loose structure. Let's start with this corner carbon atom. Let's go straight. 1 2 3 4 5 6 7. So all the rest of the carbon that is not the part of this straight line, we call that as a branch carbon. So let's try. We can write the branch carbon in a condensed form in 2 different ways. Again, the same thing. The first carbon has 3. The second carbon has 2 branching up and down. So second carbon has 2 branching with CS3, CS3. Then we have third CS2, fourth CS2. Then the fifth carbon again have a branch. So fifth carbon have CS3 group on the top, CHS3. Then we have all other things, CS2, CS2, CS3, straight line. So this is one way of writing. Second way, like we learned, you can write the branching in the same line. So CS3, then carbon, then you put two parentheses with CS3, CS3. And we know by the time I see CS3 and CS3, I know this is not the part of the straight line, because carbon, middle carbon or the center carbon cannot have 3 hydrogen attached to it. So that means it should be a part of the branch. And what's the branch? Is the carbon in front of this parenthesis always. So these two parentheses belongs to this carbon in the front. And then we have one more parenthesis that contain the branch carbon, and this carbon belongs to this carbon. So this is how you can verify which kind of branching you have, right? Let's do one more problem that we already done it before. So this is the Lewis structure. Write the condensed structure for this Lewis structure. So the time I say this is CS3, then you have carbon with a hydrogen, then we have a branch carbon atom, right? Because if I start from here, if I go like this, a straight line, this is a branch, this is a branch. So I write CH parenthesis CS3, that means this CS3 belongs to the previous carbon, which is the second one. Again you have CH, then you have to write parenthesis CS3 because this carbon belongs to this carbon on the third one, then you have CS3. Or you can show me with the bond with the branch. Second carbon has a branch, you have to show in the condensed form with CS3 on the top, and then on this carbon CS3 on the bottom. So just make sure you practice a lot about these writing these condensed structure with the branching. Now let's talk about the second way of writing beside the Lewis structure and condensed form. We're gonna learn about the skeleton line structure. So a skeleton line structure is based on the zigzag conformation of the molecule, something like this. So this is a zigzag line, and then the starting point and ending point, and the point where the two lines are connected, this line and this line. This is also a connecting point, this is also a connecting point, this is also a connecting point. These starting point, ending point, as well as the connecting point represent a carbon. So how many carbon you have in this organic compound in the skeleton line structure? 1 2 3 4 5 6 carbon. And what you're seeing over here in the skeleton line structure, we usually don't show any atom. We are not showing a carbon. Are we showing a hydrogen? No. So that means, it doesn't mean that we don't have any hydrogen on these carbon, but we are not showing it. So you should be able to understand, if I have this carbon, the first one, 1 2 3 4 5 6, if you have the first carbon, how many hydrogen this first carbon can have? Carbon always have to have 4 bond. So one of the bond is already connected with the second carbon. How many hydrogen more? 1 2 3. But we are not showing these hydrogen, right? So the first carbon has 3 hydrogen, second carbon, how many hydrogen? 2 hydrogen, 1 2, because 2 other bonds are connected with the rest of the 2 carbon atom, but we usually don't show a hydrogen over here. So this is how you normally easily calculate how many hydrogen you have in this skeleton line structure. And then if I ask you what's the molecular formula for this structure, so how many carbon? 6 carbon. How many hydrogen? Even though we cannot see it, we still have hydrogen, right? And then how would I know which formula we have to use? We have to use CnH2n plus 2 for alkane, because every bond between the carbon are single bonded. So we're still talking about an alkane. So we have to use a formula, and we will figure it out as C6H14. Right? So this is how you normally write the skeleton line structure. Right? So in the skeleton line structure, there are 2 ways you can write the skeleton line. One, when you start with an upward movement, something like this: 1 2 3 4. Second way, where you start the first two carbon as a downward motion, 1 2 3 4, something like this. So there are two ways of writing it, the skeleton structure, and both of them are correct. It doesn't matter which way you're going to write the skeleton line structure, both way of representation are correct. And then we already talk about this thing, that each point in the skeleton structure represent a carbon, and then we can easily calculate how many hydrogen you have on each carbon atom. So let's take this example. How many carbon atom in there in total? 1 2 3 4 5. So the formula is C5H12. How many hydrogen? 12 hydrogen all together in this entire structure, right? And one more thing, that sometime the skeleton line structure we call as just as line angle formula. So don't get confused if you don't get this skeleton line structure, or if you get line angle formula. Because why it says line angle? If I make any skeleton line structure line angle formula, you have a line and you have an angle in between them. So that's why the name is also as line angle formula for a skeleton line structure. So remember these two terminology too. Now let's try to do this problem over here. It says write the skeleton line structure or a line angle formula. Line angle formula for the compound shown below. So this is a space ball and stick model. Right, so this is a ball and stick model where each ball represent an element. In this case, this is carbon, this is hydrogen, and then stick normally show you a bond. Right, so this is a ball and stick model. It says use this model and figure it out, or draw the skeleton line structure. So see how many carbon you have in there: 1 2 3 4 5 6. So you have to write 6 carbon. Start with over here: 1 2 3 4 5 6. Right, so we have 6 carbon in here. Or you can go first in a downward trend, then I can make 6. 1 2 3 4 5 6. So both are the correct skeleton line structure. Right, one is in the upward trend, another one is a downward trend. So you can write in both ways. So let's take a couple of examples and learn how to draw a line angle formula of the skeleton line structure. If I say draw a skeletal line for propane, the time I see propane, prop means 3 carbon containing compound, 3 carbon, and ane means this is an alkane. So 3 carbon, 1 2 3. So this is a line angle formula, skeleton structure for propane with 3 carbon. And what's the molecular formula? C3H8. If I say draw for heptane, hept means 7 carbon containing compound, and ane is alkene again. So 1 2 3 4 5 6 7. So we have 7 turning points or dot. So that means this is an heptane formula, molecular formula C7H16. Right, if I say nonane, nonane means 9 carbon, non, right? 1 2 3 4 5 6 7 8 9. So this is a 9 carbon, right? 1 2 3 4 5 6 7 8 and 9. What's the molecular formula? C9H20. Right, if you calculate how many carbon you have in this, you will end up with 20 hydrogen and 9 carbon in this entire structure, nonane. Right, same thing for heptane and propane. So I'll show you for propane that we can confirm it has 8 hydrogen. How many hydrogen on this carbon? 3 hydrogen, hydrogen, hydrogen. On this 2 hydrogen, over here 3 hydrogen, because carbon has to have 4 bonds. So 3, 3, 6, 2, 8. So 8. But we usually don't show a hydrogen, but I just show you just for the calculation of the hydrogen. Right? Now we're going to try and write the skeleton line structure for cycloalkane. So till now we just learned about how to write the skeleton line structure for alkane. Now we're going to learn about the cycloalkane, and we already know what is cycloalkane means, right? The closed ring structure for alkane molecule. Right? So if I say draw a structure for cyclohexane, how are you going to draw a skeleton line structure? The time I read cyclo, I know this is a ring, closed ring structure. Hex means containing 6 carbon. ANE means is an alkane containing all single bond. Right? So let's make closed ring that contains 6 carbon. So I can make this structure. Right? So how many carbon you have in this structure? 1, 2, 3, 4, 5, 6. And this is cycloalkane. Why? Each carbon has single bond, right? So this is cyclohexane. How many hydrogen you have? What's the molecular formula for cyclohexane? C6H12, because the formula is CnH2n for cycloalkane, right? So this is how you make a skeleton line structure for any cycloalkane. Let's take a couple of more examples on the next slide. So if you can see this table on the right hand side, we have different name of the cycloalkane along with their skeleton line structure formula or the line angle formula. If I say cyclopropane, propane is 3 carbon. So 3 carbon in a ring structure, 1, 2, 3. Cyclobutane, butane is 4 carbon. 4 carbon in a cyclic ring structure. 1 is like a square. Cyclopentane, 5 carbon. Hexane with a 6 carbon, heptane with a 7, octane with an 8 carbon, all of them in a cyclic structure, closed ring. So this is how you make any cyclo compound using a line angle formula, the skeleton line structure. Let's try to do this problem over here. If the problem says write the skeleton line structure for butane and cyclobutane. The only difference between the two compounds is cyclo. So butane means 4 carbon, 1, 2, 3, 4. Again cyclobutane 4 carbon, but all of them are closed, right? All is a closed ring structure. 4 carbon. This is cyclobutane, this is butane. Right? So make sure you know how you draw the structure between a non-cyclo compound along with a cyclo compound. Okay, so now we're going to learn about how to write the skeleton line structure for a branch chain alkane, and we already talked about what a branch chain. So if I have any line angle formula, so you always, let's say if I have to make a branch on the second carbon, for example over here, if I have to make a branch, if you start with an upward line, then that branch will go upward. If you start with a downward trend to make a line structure, then the branch will go downward, right? But it's not the correct way. If you go in an upward trend and if you have to make a branch, you cannot go down. This is the wrong structure. You should go up. And if you're going down, you cannot make a branch up on the carbon. You go down, right? Let's take an example over here. If I have to make a branch on this carbon, should I go up or down? So let's say this strand is going downward, so we should put a branch over here, not on the top. What about the branch on this carbon? Is going upward trend, so that branch will go up, not the down one. Right, so this is how, make sure you practice a lot to make a branch chain on a line structure formula or the skeleton line structure. Let's take one more example. where should the branch will go on this carbon. So this is a downward trend, branch will go over here, right? Not in this case on the top, right? So this is one more example. So we already talk about, like, if we have to make a line, skeletal line structure, we already talk about where the branching will go up or down, right? So this is the same thing that we already talk about, so make sure you read this thing, but we already talk about this thing where you should put a branching. Let's go to the next slide. Now let's take an example. Let's say if you have a branch, but that branch contains more than one carbon atom, maybe 2 or 3 carbon. So how are you gonna make the branch? Let's take this example. You have this entire molecule, and then this is going downward, so I can make a branch downward, right? And then let's say that branch contains more than one carbon. Let's say it has 2 carbon. So these 2 carbon can go in either direction. I can go down and move the direction over here, or we can go again down and I can make the direction of the second carbon on the other side, right? So it doesn't matter which direction you are making a branch if that branch contains more than one carbon atom, right? For example, if I have one more branch on this, I can make a branch something like this, and if I have one more structure, the same molecule, I can make a branch something like this. So it doesn't matter with which direction the branch is going, as long as it has the same number of carbon atom. 1 2 3 1 2 3, right? So keep this in mind. So now let's take an example. It says write the skeletal line structure for 2 branches on a single branch point. So that means this is a loose structure, and you have the loose structure. On the second carbon you have 2 branching, one on the top, one on the bottom, and on the fifth you have a one branch that contains 2 carbon, right? So how are you going to make a line structure formula? So first you have to see how much number of carbon you have in a carbon that is going in a straight line without breaking the line. 7. So you have to make 7 point. 1 2 3 4 5 6 7. And on the second carbon you have 2 branches, right? We already learned about, but the line angle formula, the skeletal line that you drew over here, is in the upward direction. So that means you have to show the branches going upward on both sides. One is going this way and another going this way, right? So this carbon that we have contain 2 separate branches, one containing 1 carbon, second containing second carbon. So each branch has only 1 carbon, not 2 carbon. But on the 4th carbon over here, 5th carbon over here, how many carbon you have in the straight in this branch? 2. So I can make branch something like this, or I can make the same branch something like this. Doesn't matter which direction the branch is going, right? So this is how you normally do the line structure formula for the branching. Let's do a different way of writing the line angle formula. So in this case we drew the upward direction, let's do the downward direction. 1 2 3 4 5 6 7. So this is 1, this is 2 3 4 5 6 7. So on the second carbon again we have 2 branches, so this time is a downward trend. I can make 2 branch. The same carbon has 2 carbon branches again to it. So this is one way of drawing. On the 5th carbon you can make this kind of branching, right? So I already drew both ways, upward trend, downward trends. So make sure you practice, right? So let's do one more problem on this. Write a loose structure and a condensed structure for the skeletal line structure. So till now we have been doing, if we would have already a loose structure drawn, we learned about how to write the line structure. Now the line structure is already given. We have to write the loose structure as well as the condensed structure. So let's start with the line structure. So pick one end and then follow the bond. Right, so how many carbon you have in there? 1, 2, 3, 4, 5. So write the loose structure. The first carbon has 3 hydrogen and atom attached to it. The second carbon has 1 branch. So we're going up. This is a branch. Third carbon has branch that contain 2 carbon atom. This is your third carbon containing a branch that contain 2 carbon atom. Then fourth one has one more branch contain 1 carbon atom. This is 4 that has a branch. Then the fifth one has 3 hydrogen atom. So this is how you draw a loose structure. Then we have a condensed structure, CH3CH, CH3 CH. Then we have a branch. Then again on the fourth one we have a branch. Then fifth one is CH3. So this is how you can go like both ways. If the line angle is given, you can draw the loose and condense. If the loose structure is given, you can go to line, right? So you can just flip whatever the question is asking for. So now we're going to talk about a new kind of hydrocarbon, or one of the classification of the hydrocarbon, which is alkene and alkyne, and we call both of them as unsaturated hydrocarbon, right? So remember this thing. If I ask you about the unsaturated hydrocarbon, it should be alkene or alkyne. And then we already talk about what are alkene. When you have a double bond between carbon-carbon atom. Alkyne when you have a triple bond. Something like this. C triple bond, double bond is C double bond C. Right. So we already talk about this thing. So let's talk about these two unsaturated hydrocarbon, alkene and alkyne, separately and talk about their property, their structure, how to name them, right? So let's get started with the alkene. So alkene, we already talk about it, contain at least one double bond, carbon-carbon double bond, and it has the structure of this carbon-carbon double bond is trigonal planar, and we already know about if the structure is trigonal planar, the angle is 120 degrees Celsius. So that means alkene is a planar structure, right? And then this is how you normally show it in a ball and stick model, right? So this is your carbon, this is your hydrogen, right? And then this is your double bond. Over here again, this is your loose structure, and then we have an angle, right? This is one of the simplest alkene called ethene, and we're gonna learn about later on how you name it, right? Then we can also use a skeleton line structure as well as the condensed structure form to represent an alkene. Then if we use a line angle formula, so this is, if you can see over here, this is a line angle formula. So all are single bond except the one that has one more bond. So this is a double bond. For example, if I have something like this, and if I put one more line over here, so this line represent a double bond, right? And then if you see this kind of bonding, we know this is an alkene molecule. And we can also write the alkene molecule in the condensed structural formula. One, we can directly use, let's take this example, C double bond C, then we have 2C, right, with a single bond. So the time I write the first bond, CH2, second carbon has 1 hydrogen, third one has second, the fourth one has 3. The time I see this carbon has how many bond attached to it? 2 coming from the hydrogen, and then how many it need more? It need more 2. So that means this 2 is coming from another carbon in the form of a double bond, because carbon need to have 4 bond. If you see over here, the second carbon, it has just one bond from hydrogen and one bond from the third carbon. That means it needs two more bonds, so that means the two bond coming from the first carbon. So this is how you can verify or write the condensed structure, or you can specifically show a double bond in the condensed structure too. If because we know in the condensed structure we usually don't show a bond, but if you have a special bond like double or triple bond, you can show them, right? So I can write CH2 double bond CH, and then except that I usually don't show the single bond, right? So this is how you can write all the three type of structure. Now we're gonna learn how to name any alkene molecule using the IUPAC rule, right? And as well as the unbranched cycloalkene. So we're gonna talk about the naming of both of them, simple or cycloalkene. So you can read this thing from the slide, but we're gonna do on the next slide the actual example, and then I'm gonna tell you about how to name any alkene molecule. So let's go to the next slide. So let's take an example of one of the alkene. The time I drew the line angle from the skeleton line on the left hand side, I can see this bond over here. The time I see a double bond, I know this is an alkene. So how you name an alkene molecule? The first step is you always have to include a double bond when you start counting the number of carbon atom in that molecule, right? Second rule says you always give the priority to the double bond. You always have to start counting so that the double bond will get the lowest number when you start counting, right? So let's take these the two rules that we just talk about, right? You can write it down in your notebook, whatever I told you, and then apply the same rule. So let's try to name it. So we see have double bond over here, and this is a corner carbon. So we have to start counting from here, 1 2 3 4 5 6, not from here like this, 1 2 3. We cannot count from here, because if you count from here, then your double bond will get a 7, right? So it's not possible because we already getting a double bond on the first carbon. So we have to give the priority the lowest number on the double bond, right, containing carbons. So let's remove this number and let's start counting. So this is 1 2 3 4 5 6 7 8. The time I see 8, if you have 8 carbon containing compound, I know that name is oct, and this is an alkene because this is a double bond. The ending word will always end with ene, so octene, right? And then the time I see this is octene, I know that compound is an alkene and we have a double bond. But where we have a double bond? It can be over here, it can be in between 5 and 6. How would I know where the double bond is if we don't have this structure in front of me? Then we have to specify the location of the double bond. We have to tell the double bond is present on the first carbon. So we have to specify 1. This is the location of the double bond. Right. So you always take the carbon before a double bond, right? So first carbon is before the double bond, so we have to write 1 octane. But there's another way of writing. If you don't write 1, it's okay, but if you don't write an octane, everyone would assume that it's on the first carbon, because we usually don't write a number if it's on the first carbon, right? So make sure if it's on the first carbon, it's up to you whether you write 1 octane or just octane. But if the double bond is anywhere except on the first carbon, you always have to specify the location. For example, we'll do some more example later on, but this is a concept that you need to worry about, right? Let's take one more example over here. If I have this structure, what's the name. So now we'll see, we have two free end, this is a free end, this is a free carbon. I can start counting from the free end, not from the center. You cannot start counting from this carbon because we have a double bond on this. We cannot start, we always have to start from the corner carbon, right? So it's up, let's see which end we have to start counting. Let's start counting 1 2 3 4 5. So the double bond is coming on the third carbon. If I count from here, let's say if I count from the other way around, 1 2 3 4 5. So if we count from here, the double bond is coming on the second carbon. So which way we have to start counting? We have to start counting from right to left, from this side. So the right way of counting is the blue one, 1 2 3 4 5. And the naming will be, if you have 5 carbon, 5 is pent, because this is an alkene, pentene, ending word is ene, and then you have to specify the location of the double bond, where the double bond is on the second carbon. So the name is 2-pentane, right? Let me tell you one more time why we didn't start from left to right counting, because from left to right double bond is occurring on the third, and we have to give the lowest number on the double bond. That's why we started the counting from right to left. Okay, so this is how you normally do for a non-cyclo one, but how would you name the cyclic compound? So if you see this example over here, we have a cyclic alkane, or cyclic alkene. Why? This is a cyclic compound, and the time I see this double bond, this is an alkene, ene, so this is cyclic alkene. And now we have to give the lowest number to the double bond, so you can start counting from here, 1 2 3 4 5 6 7 8, or you can start counting like this, 1 2 3 4 5 6 7 8. So in this case it doesn't matter. Why? Because if I start counting over here 1 in the red, then the double bond is occurring on the first carbon, right? If I started with the blue, 1 2, again the double bond occurring on the first carbon. So it doesn't matter which way, clockwise or anti-clockwise, which way you're gonna count, it doesn't matter, right? So we have to write the name, we have to write cyclo, because this is a cyclic compound. 8 means oct, and this is an alkene, ene, so that means cyclooctane. And we usually don't write 1 because we are assuming that if nothing is written, this is on the first carbon, right? So you can write 1 cyclooctane or just cyclooctane, it's up to you. Let's take this example and then try to name this molecule. So we start from where we start counting, from here or from right to left? We have to start counting from here, 1 2 3 4 5, because we have to give the lowest number to the double bond, right? So we have 5 carbon, pent, and then this is an alkene, ene, ending word, and then the double bond is present on the first carbon, so 1-pentene. What about the B? It's a cyclic compound. The time I see this is a double bond, I know this is cycloalkene, and then we can start counting like this, 1 2 3 4 5, or you can start counting like this, 1 2 3 4 5. It doesn't matter because the double bond will always be occurring on the first carbon, the lowest number. So we can write cyclopentene, right? It's a cyclic compound. So this is how you normally name different alkene and cycloalkene. Then we have some other term called dienes and polyenes. Is the same is a compound containing multiple double bond. If the compound contains 2 bonds, then we call as diene. Di means 2, poly means many. So if an organic compound have only 2 double bond in there, then mean that compound is a diene. If any molecular compound contain more than 1 double bond, that means that compound is polyenes, right? For example, this beta carotene has how many double bond? Double bond, double bond, double bond. It has multiple double bond. So this is a polyene. So let's take an example and figure it out whether those compound that is given over there, whether it's a diene, simple alkene, or polyene. That I might see how many double bond you have in there. 2 double bond. So diene. If you have just one, is a simple alkene, and if you have more than 2, polyene. So this is how you can figure it out, which kind of alkene is that one. So now we're going to talk about a special kind of isomer that is present in an alkene called geometric isomer. And why alkene show this kind of isomer? Because carbon-carbon double bond are not free to rotate like we have in carbon-carbon single bond. If you remember, which kind of isomer we can form if you can rotate a single bond in alkane, conformation isomer. But in alkene, we cannot rotate around a carbon-carbon double bond. So because of that, we have a special isomer called geometric isomer. So it says 2 alkene can have the same chemical formula and same connectivity of atom, but a different 3D orientation around the double bond. What does it mean? Let's take this as an example. So let's say this is any alkene molecule that has 2 compound A and A, B and B attached, and we have a carbon-carbon double bond. So if I hold this carbon steady, if I want to rotate this carbon across this double bond, we cannot rotate. And because if we cannot rotate, this AA molecule will be on the same side always, and BB will be on the same side always, until or unless we break this A and B and replace with each other. We have to break the bond because we cannot rotate the molecule, right? So this kind of isomer are geometrical isomers, right? So for example over here, because we cannot, no rotation possible, we cannot rotate the second carbon, and if we cannot rotate the second carbon, then A and A won't be in this orientation because we cannot rotate this thing. A will always be on the top, right? So that means if I write the formula for both the compound, what's the formula for this compound? C2 A2 B2. What's the formula for this compound? C2 A2 B2, right? Same chemical formula, both of them has same chemical formula and the same connectivity. If you can see over here, carbon 1 connected with A and B, carbon 2 connected with A and B, same thing. On the second structure where you have A in the opposite direction, again carbon 1 attached to the A and B, C, same thing, A and B. So the connectivity is also the same, but they are different in the orientation around a double bond. Means in the one of the orientation, both A is on the same side, B is on the same side. In the second structure, both A are on the different side, up and down. Same for B, up and like in different side. So that means they are showing geometrical isomer. Now geometrical isomers can be of 2 types depending on the structure of the geometrical isomer. One of them is cis, second one is trans. So we're gonna figure it out. What is this geometrical isomer? What is trans geometrical isomer? So each carbon atom in a double bond must have at least 1 hydrogen and 1 carbon. Means let's take this example over here. You have a carbon-carbon double bond, right? On each carbon you have at least 1 hydrogen, and then the second bond on both the carbon can have any group. In this case we have CH3 group, right? So if both the hydrogen are on the same side, in this case is on the same side, and both the group are on the same side, that means this is cis isomer. But if the hydrogen are in the opposite direction across a double bond, or the groups will also be in the opposite direction, right, different direction, right, or they are in different space. Over here, hydrogen on the top, hydrogen on the bottom, on the second carbon, they we call as trans isomer, right? So geometrical isomer can be cis and trans, and you can easily verify depending on where you have the hydrogen and the group attached to the carbon. So let's take some example on the next slide and try to figure it out, which one is cis, which one is trans. So let's take this example over here. Label these pair of compound as cis isomer, trans isomer, or same compound, right? So if I have this compound in A, so let's say this is a carbon double bond, right? And then this carbon has one group which is carbon, this carbon also attached with a carbon, and how many hydrogen both of these carbon has? One hydrogen, in this case on the same side. So if you can see that both the hydrogen are on the same side and both the group are on the same side, this is a cis isomer. What about over here? You have a double bond, you have a carbon over here. So one of the carbon attached to the carbon double bond is over here, another one in the top. So the groups are on the opposite side, up and down, and the hydrogen is also up and down on this. So this is trans isomer, right? They are not on the same side. What about this one, B? If you have this compound 1 2 3 4, this one, and then if you have the second compound, what's the difference between them? Is nothing, because if you start from this end and if you go all the way, you end up with this, with the same number of carbon. If you start from this end, you end up with this end, you have all the carbon atom covered, right? And all of them are single bonded. So that means why you have the structure upward in over here, because of the rotation around the single bond. So they are conformers, right? They are the same compound, they are in conformers or conformation of each other, but the top one are isomers of each other, geometrical isomers. Now we're going to talk about the third type of hydrocarbon called alkene. And the time I see alkene, we know it has a triple bond, and this is an example of a triple bond alkene where you have carbon triple bond in there. And then what's the shape of this triple bond or alkene? Is in a linear geometry. And if you have a linear geometry, what's the angle? 180 degrees angle between the bond. So the angle is 180, right? So how you can draw the alkyne structure in a line angle formula, Lewis structure, or condensed structure? So in the skeleton line structure formula, you normally show an alkene with a straight line without any angle. You cannot draw a triple bond something like this. You always have to show in a straight line, and then you have a carbon across a triple bond. So you have one carbon over here, you have one carbon over here. And why you have to show a straight line or linear line? Because triple bond has a linear shape. That's why this linear line denote the shape of this triple bond, right? Then for the Lewis structure, again you have to show the triple line. For the condensed structure, you have to show the triple bond, or you have to just see carbon without any hydrogen attached to it. So there are different ways you can show a triple bond. Now we're gonna learn about how to name an alkyne molecule like we did for alkane and alkene. We're gonna focusing on how to name according to the IUPAC name, right? So according to the rules, for naming an alkyne, You have to use the same rule that we use for alkene, but the only difference is the ending word will be YNE, not ENE, right? That's the only difference. And then there is no geometrical isomer possible. Why? Because it is a linear shape. If it's a linear shape, you cannot say which one is on the top, which one on the bottom, or which one on the same side. So no geometrical isomer is possible for alkyne molecule. So now let's try to name couple of the alkyne molecule according to IOPIC name. You have to apply the same rule like I said, like we did for alkene. The only difference is over here in alkene we have a double bond, in alkyne we have a triple bond. So you have to give the lowest number to the alkyne or the triple bond whenever you start counting the carbon. There is no way you can put a larger number on the carbon containing a triple bond, right? You always have to give a lowest location. So we have two free carbon atom, one over here, one on this side, which end we have to start counting from right to left or left to right. We have to start counting from this carbon because we have to give the lowest number to the carbon containing a triple bond. So 1 2 3 4 5 6. 6 is your hex, and then because this is an alkyne, your ending word will be Y and E, hexyne. So 1 hexyne. And what is 1? 1 is the location. We're telling you that the triple bond is present on the first carbon. Let's try to name these other two molecules. So again, you have a line structure formula, skeletal structure formula. Now we have two free carbon. We can start from here, or we can start from this carbon that has a triple bond. So we have to start from this carbon because we have to give the lowest number to the carbon that contain a triple bond. Again 1, then this is the second carbon, 3 4 5. And if you remember why this is a linear shape, because triple bond is a linear structure. That's why you always assume that you have a carbon across a triple bond. That's why I put carbon number 2 over here, even though we don't have any angle or any joining of the bond, right? So make sure you don't forget to count the carbon number 2 across a triple bond. So again, this is 5 carbon, 5 is pent, triple bond Y and E, 1 pentyne, triple bond on the first carbon, 1 pentyne. Let's try to name the third one. So now again we have a problem. We can start the counting over here, we can start the counting from here. Can I start counting from the center carbon? No. If the triple bond or a double bond is not present on the corner carbon, you cannot start counting from the center carbon to give the number 1. So you have to decide which end you have to start counting so that the triple bond will get the lowest number. So if you start from here, 1 2 3, so the triple bond is getting 3. If I would have started on the other side, 1 2 3 4, now the triple bond will get the number 4, but we already getting 3 from this side, so we have to start from left to right. This is the wrong way of counting, so I'm just clearing this up. So we have to start counting 1 2 3 4 5 6 7. So 7 is hept, alkene is YNE, heptyne, and you have to locate where the triple bond is on the third carbon. So 3 heptyne. So this is how you name any alkyne molecule. Now we're going to talk about another type of hydrocarbon called aromatic hydrocarbons. So what are aromatic hydrocarbons? So previously it was discovered that most of the compound that gives an aroma contain a special type of structure, right? Something this kind of structure with alternate single double bond, right, with a 6 carbonate. So it was found out that all the compound that gives like some kind of scent or aroma made up of this special structure. That's why all the compound that containing this kind of structure, we call that as aromatic compound or aromatic ring, right? and then this is shown in the red over here with a carbon, double bond, single bond, alternate double single bond, right? And you can find this kind of aromatic ring or a compound in vanillin, found in vanilla beans, right? Because they can give you an aroma. But later it was found out that it is not the case. There are many compounds that are not aromatic, that cannot give you any kind of smell, but still they can have this kind of structure present in there, but the name stuck with it, aromatic compound. So from now on, if I say aromatic compound, you should be knowing that I'm talking about a 6 carbon ring with alternate single double bond. That's your aromatic ring. So from the last slide, we just learned about what are the aromatic ring. So aromatic ring, we have a special name for that ring. We call that as benzene. So aromatic ring present in the compound we call as benzene ring, right? And what's the formula for benzene? C6H6. If you count each, how many carbon you have in there? 6. How many hydrogen? 6. And then each carbon has all is octet full. So this is the formula for benzene. So in the simplest aromatic compound that contain a benzene ring, we see that we have alternate double bond, single bond, then double, single, alternate ways, right? But it was found it out experimentally that this is not a double bond and this is not a single bond. What the scientists figured out that the bond between all of the bond is not double and single. They have a special kind of bond that we have 1.4 bond. That's an average between 2 and 1, right? And then it was already seen that all the 6 electron, how many double bond you have in there? 3 double bond, and each bond represent 2 electrons, so total of 6 electrons. So it was found out that all the 6 electron in the double bond is shared by all the 6 carbon, right? And then this kind of shading we call as delocalized electron. And because of these two delocalization electron, this aromatic ring or a benzene ring are stable. And if they are stable, they are not reactive because they are stable. So what does it mean? In a benzene ring, it was found out there is no double single bond. What does it mean? They are flipping it their places. So sometimes this bond is a double bond, sometimes the bond goes over here and make this double, and this one come over here. So that means the double bond is keep on revolving around all the 6 carbon and making the electrons in the double bond as delocalized. They are not localized at one place. And the time you see this kind of movement of the double bond, you will see a benzene ring normally be shown as in the form of circle. This is also a benzene ring. So this circle represents the electrons are revolving in the double bond, are revolving so fast they are making, you cannot tell where the double bond is. So that's why you are just showing a circle in the at the center. So this is also a benzene, right? And this is we call as delocalized electrons. So now we're gonna see what's the difference between benzene and aromatic ring with a cyclohexane. So if you see the time I see benzene, this is a alternate double single bond, or the best way of representing is something like this with a circle, right? Because the double bond is flipping so fast, right? And if I draw the cyclohexane, the time cyclo is a closed ring, hexane is a 6 carbon. What's the difference between benzene and cyclohexane? You don't have any delocalization of electron. Delocalization of double bonds, double bond electrons. right? So you have just simple alkane with a closed ring. And then if you see over here the molecular formula, benzene C6H6, cyclohexane C6H12. So that represents that none of the carbon has a double bond in there, right? If I give you one more example with a cyclic ring, but in this time if I put just one single bond, this is cyclohexene. This is also different than benzene. So make sure you know the difference between benzene and all other cyclo compound. In a benzene you will always have alternate single double bond, or a circle is present in the center of the cyclohexane, right? So this kind of structure or this kind of structure. So let's do this problem over here. The problem says draw the Lewis structure of the benzene. I know the time I say Lewis structure, you have to show the carbon. So you have carbon, 6 carbon in a closed ring, and then you have alternate double, single, double, single, double bond, and you have one carbon on each carbon atom, hydrogen on each carbon atom, right? If the problem would have asked you draw the line angle formula, you can draw it something like this, or something like this. This is your line angle, skeleton line structure, you can say, and this is your Lewis structure. So now we're gonna learn about, so till now we just learn about naming of the simple hydrocarbon, where you have to just count the number of carbon atom and then just write it down, the name accordingly, whether it has a single bond, double bond, or triple bond. Now we're gonna learn a little bit more complex structure of a hydrocarbon called substituted hydrocarbons, and we're gonna use the IUPAC nomenclature and figure it out how to name any branch chain hydrocarbon. So let's go to the next slide and then try to name one of the hydrocarbon which is substituted, and then we'll try to learn the concept. So before we go on the naming, let me give you an example. Let's say if you have any skeleton line structure, and then if you have this line on the top, so what is substituted mean? So if you start, how many free end carbon you have in there? You have this carbon which is free, this carbon is free because there is no carbon attached to this carbon, and this carbon is free. So we have to, if I start from here and then if I follow the bond, now I have a two choice. I can go up or I can keep going straight. If I keep going straight, then I included 4 carbon. I didn't include this carbon in our counting. So this carbon which we normally don't count in a chain, we call that carbon as a substituted carbon. So any carbon which is not the part of the original counting of the carbons are substituted carbons, right? So let's take this concept and try to follow the rules. How to write the substituted alkane name. So the first thing, identify the parent chain. What is parent chain? Parent chain is the longest continuous chain of carbon. So in the top example that I gave it to you, what's your parent chain? Parent chain is this chain that I counted down. How many carbon you have in there? 1, 2, 3, 4, the maximum, right? If I would have gone up, let's say if I would have gone something like this, 1, 2, if I would have gone up, then we would have just 3 carbon. But I already know if I would have gone the same way that I did, I got 4 carbon. So our parent chain is the longest continuous chain of carbon. So I got 4. So this is our parent chain for this. Parent chain. And what's this? Carbon on the top. That's your substituted carbon, which is not the part of the parent chain. Right. Let's apply the same concept over here. So you have this carbon ending this carbon and this carbon. If I start counting from here, 1 2, now I have a choice. I can go up or I can go straight. Which way should I go? If I go up, I got only 2 more carbon, so 1 2 3 4. But if I would have gone straight, I would have gotten 1 2 3 4 5 6 7 8 carbon, right? So I can get, if I go straight, I can get 8. If I go this way, I can get 4. But if I start from the top, this is also a free carbon. If I go this way, 1 2 3, now I can go left or right. I should go right because I can see multiple carbon over there, right? Because we need to put as many carbon atom in a chain without breaking the line. So if I go like this, 1 2 3 4 5 6 7 8 9, so this is the maximum carbon I can include without breaking a line with this sequence. So I can say easily that this one is your parent chain, the carbon within this green box, and we have 9 carbon in there. So this is parent chain because I included the maximum number of carbon. And what about this carbon, which is not the part of this box? This is your substituted carbon, right? So this is how you can get the substituted one. So the rule, second rule says, the first rule says you have to figure out the longest possible chain to get to name as a parent chain, and all the carbon that is not the part of the parent chain is your substituent. The second rule says sometime what happens that you get, if you count the number of carbon in a parent chain, you will always get the same number of carbon atom, right? It doesn't matter where you start counting it. For example, if I start from here, 1 2 3 4 5 6, I got 6 carbon. I could have started counting from this side, 1 2 3. Now I have a choice. I could have gone up, or I can go right now up or down. So if I can see, if I go down, I have more number of carbon atom in there. So 4 5 6, right? So it doesn't matter. If I start from over here, I got 6 carbon. If I start from this carbon 1, I got 6 carbon. So I have a tie. Which parent chain should I consider? Because both of them has 6 6. So the rule says if there are 2 chain of equal length, the maximum number of carbon that you can include, select the one with more substituent to be on the parent chain, right? So the concept is, if I take the parent chains this way, the original number that the publisher already given you, if I use this parent chain, how many substituent we have? How many carbon atom is not the part of this parent chain? This is the carbon which is not the part of the parent chain. This carbon not the part of the parent chain. So I got 2 substituent or substituted 2 substituent, right? But if I would have used the second way that I counted for you, 1 2 3 1 2 3 4 5 6, how many substituent I got? Just 1, which is present on the third, right? So if you have the parent chain with the equal number of carbon atom, you always choose the parent chain that has more number of substituent attached to it, right? So this is the right way of counting, 1 2 3 4 5 6. This is not the right way of counting because you have just 1, right? So this is the correct way, and this apply only and only if you have same number of carbon in the parent chain, and you have to decide which chain we're going to use as a parent chain. So now we already learned about how to figure out the parent chain. Now let's say how to name any substituent. So let's say if this is your chain, this is your substituent, I start 1 2 3 4, then this is my substituent which is not the part of the counting. So always remember this thing, your substituent name will always end with YL. Substituent we always call as alkyl. So alkyl can be any number of carbon. 3 carbon atom is propyl, 2 carbon atom is ethyl. So the naming is always end with YL, right? YL ending. So what's the name of this substituent? How many carbon atom? One is meth. So the name is methyl. What about this one? If I have any random this kind of substituent, how many carbon in this substituent? 1, 2. So 2 carbon is eth and YL, ethyl. So this is how you name a substituent. Let's take a couple of more example of the alkyl group. If this is your substituent, how many carbon in there? 1, 2. 2 is your eth. Ending word will be YL, ethyl. How many carbon on this? 1, methyl. Right. So this is how you normally do it. We already done it right on the previous slide too, but just to have an idea, right, how you do it. And what about this one? Right. So this is 1, 2, 3, 4. These 2 carbon is not the part of the counting or the parent chain. So what should be the name? So if I see the second carbon has 2 separate substituent, this is not in the connection. So this is 1 carbon, this is 1 carbon. So both of them is methyl group. Methyl, right? METHYL. And then make sure you make a difference between why this is ethyl, why this is ethyl, why not methyl. So make sure you know the difference. So now let's try to name any organic compound with a substituent and see how we can name an organic compound if you have multiple substituent attached to the organic compound, right? So let's go to the next slide, and then you can read all the information from here, but I'll explain you on the next slide how to name it if you have the multiple substituent attached on the parent chain. So let's take this example over here. So this is an organic compound, right? Then the first rule says we have to count the maximum number of carbon atom without breaking up the chain. So I can start from here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the maximum number I can get in this entire structure without breaking up the bond, right? So this is our parent chain. I made a box, and then the rest of the 2 carbon atom, this is your substituent. 1 carbon atom substituent, because this is not the part of the counting. So right, so now the question is why we started the counting from this side, 1, 2, 3, 4. Why we didn't start counting from this side, 1, 2, 3 all the way 9 on this side? So according to the IOPIC rule, it says you have to start counting from that side so that the substituent will get the lowest number. Or lowest location number, right? So if I would have started from here, 1, 2, 3, 4, the first substituent is occurring on the 4th carbon. But when we started from here, 1, 2, the first substituent is occurring on the 3rd carbon. So we have to give the lowest number to the first substituent that is occurring on the numbering. So the 3rd comes first, then 4. So we have to start counting from right to left, right? So we already covered this thing. We cannot start counting from here. We have to start counting from this side upward, from right to left. Then what should be the name? Then we normally name the substituent alphabetically. Right, so whichever substituent name comes first alphabetically, we write that name first. So let's write the first substituent over here that has one carbon. What's the name? Methyl. What's the name of the substituent that has two carbon connected? Ethyl, because eth, two containing eth, and yl is because it's a substituent. So which comes first in the alphabetical order? E comes first, right, in the alphabetical order. So we have to write ethyl, methyl. Then you have 9 carbon. 9 carbon is non, and because this is an alkane, nonane. Right. The other important thing is that the time you already wrote it down, the substituent name alphabetically, you have to tell me where these substituents are present on the parent chain, on which carbon. So you have to include the location. Ethyl is present on the 6th carbon, and methyl is present on the 3rd carbon in the counting, and you have to separate the number from the alphabet by a hyphen, right? 6 hyphen ethyl hyphen 3 hyphen methyl, nonane. So this is the right IUPAC name for this molecule. Let's take this example one on this slide, right? So according to this example, we have the parent chain 1 2 3 4 5 6, and then this is not part of the substituent, this is also not part of the substituent. So this is a methyl group, this is methyl group, right? So now why we started the counting from this side? Why we cannot start counting from this side 1 2 3? Because if I would have started from right to left, something like this, 1 2 3, the first substituent occurring on the 4th carbon, but over here it occurring on the 2nd carbon. So we have to include the counting from left to right this way, right? So on the 2nd carbon you have methyl group, on the 3rd carbon you have the methyl group one more time. So you have two substituent on 2nd and 3rd, but both the substituent has the same naming, methyl methyl, right? So if you have the same substituent on the parent chain, right, depending on how many times it occur on the parent chain, you have to use a prefix called di, tri, tetra. Di means that substituent occurring 2 times, tri means 3, tetra means 4, right? So I can write this name something like this: 2-methyl, then parenthesis 3-methyl, and then how many carbon in total in the parent chain? 6 carbon, hexane, because these are alkane. So I could have written something like this: 2-methyl, 3-methyl hexane, but according to IUPAC rule you cannot write the same naming, methyl methyl. What you need to do, you have to just include the location where the two substituents are present, 2, 3, and then to save time to write again and again methyl methyl, I write di, because you have the same methyl groups, dimethyl hexane. So from this naming, this is the right naming, from this naming we can say we have 2-methyl group, dimethyl, 1-methyl group is present on the 2nd carbon, 2nd methyl group present on the 3rd carbon of the parent chain. So this is how you normally do it. And we already talk about that the substituent should be written in alphabetical order. So we already talk about this thing. For example, if we have 6-ethyl, 3-methyl nonane, previously why we wrote it down 6-ethyl and 3-methyl first? Because E comes first, then M-methyl, right? So we already talk about this thing, but keep this in mind, right, whenever you're writing the substituent. Now let's try to take some more example how to name any organic compound with a substituent. Let's say if you have this compound, how you name this organic compound or this hydrocarbon. So the first step is figure it out what's the parent chain, right? The maximum number of carbon without breaking a bond. So we have 3 free and we can start counting from this side. We can start from here and here. So let's start counting. 1, 2, 3, 4. I can go up, but I can see there is only 2. But if I go straight, I have 3 more. 5, 6, 7. Right? If I can start counting from here too. I can say 1, 2, 3. I can go left and right. If I go over here, 4, 5, 6. Or if I go on the other side, 4, 5, 6. So the maximum number of carbon atom that we can get in this structure is 7 in the blue form, right? The blue counting. So that means we're going to start the counting from left. So we have to use this our parent chain, the maximum number of carbon. That's your parent chain. And now this is not the part of the parent chain, this is a substituent. And then how many carbon you have in there? 2 carbon. 2 carbon is ethyl, right? So our substituent is ethyl. Now the problem is which end we have to start counting. Is the one that we started counting is already right way of it, or we have to start from left to right? Which way? So if I start again 1, 2, 3, 4, the substituent occurring on the 4th carbon. If I would have started from the right hand side, 1, 2, 3, 4. So in this particular case, it doesn't matter which way you have to start counting because the substituent is occurring on the 4th carbon on both sides. So for this particular case, it doesn't matter. So we have to write a substituent name with the location. On the 4th carbon, I have an ethyl group. And then you have to write the parent name. You have 7 carbon. 7 carbon is hept. And all of them are alkane. Single bond heptane. So 4 ethyl heptane. So this is how we normally write the name. Let me give you one more. What's the name of this compound? So if I start from here, 1, 2, if I go up 3, I go 3. No, we cannot go because we still have this 3, 4. So we have this as our parent chain, right? 1, 2, 3, 4. Or I can start counting from the other side too. I can use any of this carbon and start counting. 1, 2, I can go down, I can go up. I know this is just 1 carbon. I should go on the right hand side. 3, 4. So this is the again 4 carbon, right? If I start from here, 1, 2. Now I have a choice. I can go up, I can go down, or I can go straight. I can see if I go straight, I have 2 more carbon instead of 1 on both sides. So I can go 3, 4. So it doesn't matter which carbon atom you're starting with, you will not get more than 4 atoms in this entire molecule. So this has to be a parent chain with 4 carbon. Now I would recommend always choose a parent chain in a straight line if you have a tie of maximum number of carbon atom. So I am choosing this as our parent chain with a 4 with a green numbering, and I am taking out everything else. And now I have 2 substituent. This is 1 substituent, this is your second substituent. Both is 1 carbon, which is methyl. This is also methyl. So I can write the name. I can say 2-methyl. On the second carbon I have a methyl group. On the second carbon again I have a methyl group. And 4 carbon is but. and this is an alkane, butane. This is one way of writing, but according to the IOPIC, if you have two same substituent, methyl, methyl, ethyl, ethyl, it doesn't matter. If you have the same substituent attached, you should write the location on the second carbon, comma, on the second carbon you have dimethyl, 2-methyl group, and then butane. So this is the right way of writing the IOPIC name, because you are specifying the location of both the substituent, both on the second carbon. So now we're gonna learn about how to name any substituted cycloalkane. So till now we just learned how to write the name of the simple substituted alkane. Now we're gonna use a cycloalkane if you have any substituent attached to it, right? So let's go to the next slide, and then we'll see how we start naming of an substituted cycloalkane. So let's take an example over here. You have a 6-carbon closed ring, right, and you have one substituent attached to it, right? So we'll always consider, right, for this particular class, you consider this cycloalkane as our parent chain. So what's the name of parent chain? You have 6 carbons, cyclohexane, then which is not the part of the parent chain is your substituent, right? So methyl is your substituent. You can write methyl cyclohexane, right? So this is how you name it. The second way is if you have more than 2 substituent attached to it. In this example over here, you have 2 substituent attached, one over here, one over here. Now the question is, both of them is methyl substituent, and what's your parent chain? Cyclopentane. You have 5-carbon closed ring structure. That's your parent chain. So again, you have to start counting such a way that both the location or both the substituent will get the lowest number. So the lowest number that you can give to any of the substituent is 1. You have to start counting. So if you're getting this as 1, then you have to start counting clockwise, so that the other substituent will get the 3. You cannot go the other way around. If you would have gone the other way around, then the other substituent will get the 4, right, which is not possible because we are already getting a 3. So that means this is the correct way of counting. So the numbering or the naming will be 1,3 dimethyl. I'm saying on the 1 and on the 3rd carbon of this cyclopentane, I have 2-methyl group, dimethyl group. So this is how you do it, 1,3 dimethyl cyclopentane. The second naming 1,4 dimethyl cyclopentane is wrong. Why? Because the second substituent we are already getting on the 3rd one, so 4th is not possible. So this is how you normally calculate or number the system if you have more than one substituent. So let's take an example on this. Write the IOPIC name of the following branch chain alkane. So this is one of the branch. If I start counting from here, 1, 2, 3, 4, 5, 6, 7. If I would have started from the other side, 1, 2, 3, 4, 5, 6, 7. So it doesn't matter. You will always have 7 carbon in your parent chain, and the substituent is occurring on the 4th carbon. Doesn't matter which end you are starting counting in. So the naming will be on the 4th carbon methyl. You have 7 carbon heptane, 4-methyl heptane. What about the second one? How many free carbon you have? You have 1 free carbon over here, the ending carbon. You don't have any carbon attached to it, right? You can start counting from this carbon. You can start counting from this carbon and from this carbon. So let's start from left to right. If I go over here, 1, 2, I can go straight, I can go up. So I'll go straight because I can see 2 carbon in the straight, one on the top. So I need to have more than maximum number of carbon atoms. So I'll go over here, 3. Now I have a choice. I can go down, I can go straight. The time I see I go straight, I have just 1 more carbon, so I should go down because I have 2 more, 5. So the maximum I can get is 5, right? So that's why it's pentane. And on the second carbon you have methyl group. On the third carbon, this is not the part of the counting, right? So this is a substituent. This is a methyl group. So on the second carbon, on the third carbon, both of them is methyl methyl. So dimethyl pentane. So this is how you normally name any compound or hydrocarbon. Now we're gonna learn about, till now we just learned about the substituted alkane naming, right, where you have all of them are single bonded. But now we're gonna learn about how you name any substituted hydrocarbon which is present on an alkene and alkyne, right? So let's go to the next slide and then we're gonna learn about how we name it. So if you have this structure, let's try to name this structure. The rule says you have to include double or triple bond in your parent chain. You cannot leave double or triple bond if there is any from your parent chain counting, right? The second rule says you have to give the lowest number or location number to a double or triple bond if there is any present, right? So let's apply the rule, both the rules, and then rest of the rule will be the same as like we did for alkane, for the substituted alkane. So let's try it this one. So for this structure I can write the numbering two ways. I can start with this carbon 1 2, I can go this way 3 4, or I can go this way 3 4, doesn't matter. So this is your parent chain, maximum number of carbon, and then this is your substituent. This is one way of counting. Second way of counting is I can start from the corner and keep going straight, and I can get 5 carbon, which is more than 4 in the previous structure. As both of them are same structure, then this can be our parent chain. So what's wrong with this? Why we cannot have this as our parent chain even though we have high number of carbon atom in there? We have 5. In the previous one we have 4, but still I'm using this as a parent chain because the rule says you cannot leave out the double bond. Second, you have to give the lowest number to the double bond. In the second structure we are leaving out the double bond. We are not including a double bond in our counting, right? So this is a violation of one of the rules. The second rule says you have to give the lowest number to the double bond. Over here we are giving the number 3 to the double bond, right? So both the rules are violated. So that's why we are not using this counting. We have to use this counting 1 2 3 4. So the naming will be, on the second carbon you have 2 carbon as a substituent. 2 carbon is ethyl. So you have to write on the second carbon you have an ethyl group, and then 4 carbon is butane, but this is an alkene, that's why it's butene, and you have to specify where the double bond is in your butene parent chain on the first carbon. So the naming will be 2 ethyl 1 butane, right? And the same thing apply for a triple bond. You cannot leave the triple bond, and you have to give the lowest number to the triple bond when you start counting for the parent chain. Let's try to name these 2 branches, right, of hydrocarbon. So I have a double bond over here, I can see it, and I have a double bond over here, I can see it, right? So that means this is an alkene, and we have to include the double bond in our counting when we count for the parent chain. Second, we have to try to give the lowest number to the double bond. So if I start from here 1 2 3, if I go down I have just one more carbon, but I can see many more on the right hand side, so I have to include as many as possible. 4 5. Now if I go up 6 7, if I go down 6 7, it doesn't matter for this case. So let's go this way 6 7. So if I count this way, I'm giving the double bond as number 4, and I'm including in the counting, but I'm giving 4. Let's go the other way around. If I start from here, 1 2 3 4 5 6 7. If I started from here, I'm giving the double bond as number 3. So this is the right way of counting it, right? The blue one. So, and we have 2 substituent. One substituent is over here, which is ethyl. This is not the part of the counting, right? And this carbon is also not the part of the counting. This is methyl. So let's try to name it. And then if you have 2 substituent, you have to write alphabetically. So you have to write 3 ethyl, third carbon has an ethyl group, hyphen 5, fifth carbon has methyl, and then 7 carbon in your parent chain, heptene. And the time you're saying ene, you have to specify where the double bond is on the third carbon, right? So that's why. So don't forget to write where the double bond is, write the location. Let's try to do the second one. So we start from here. You can start from the top 2. 2 3 4 5 6, right? The second way of counting is 1 2 3 4 5 6. So which way is the correct way? The one that we did before in the red color. Why? Because I'm giving the second number to the double bond, where in the blue one I'm giving the 4th number. So the 2 is higher, right? The lowest one that we can get. Then we have 2 substituent. One is over here, methyl. I have one over here, methyl, as a substituent. Then I can say on the second carbon, on the third carbon, I have the same substituent, methyl, so dimethyl. And then on the second carbon, I have a double bond, and we have 6 carbon, 6-hexene. Right? So this is how you normally write the name of the second one. Now let's try to name a substituted benzene. So whenever you have a benzene and a substituent attached to it, you always treat benzene as your parent chain, right? And then if there is only one substituent attached, you don't have to give the location number of that substituent, because there is only one, so it's supposed to have 1. If you have many substituted benzene, then we have some common names for that, right? So let's take some of the example. You have a benzene, then you have one substituent carbon attached to it on the benzene. So you have to just write the substituent name, methyl benzene. Benzene is your parent chain. Right? And we have a common name, methyl benzene, we have a common name called toluene. So if I say toluene, I'm talking about methyl benzene. Now you have a substituent as a ethyl, then ethyl benzene. If you have 3 carbon attached to the benzene, propyl benzene. Right. Now let's talk about the benzene, substituted benzene, when you have more than one substituent. So let's take this example over here. You have a benzene and you have 2 substituents, methyl and ethyl. So you have to always write alphabetically, right? So you have to give number 1 to the ethyl. Why? Because E comes first alphabetically compared to the M. So remember this thing. If you have more than one substituent, you have to give the numbering alphabetically. So 1 ethyl, 3 methyl benzene, right? And why I count it like 1 2 3, why we didn't count as like 1 2 3 4 5 6, because the second substituent is going to come on 5th, not in 3. So that's why we did counterclockwise. Let's take one more example. Write the IUPAC name of the following benzene substituted structure. Then let's say this is your benzene and you have 2 substitution. This is how many carbon? 1 2 3 4. 4 is butane, butyl. 1 substituent, 1 carbon, methyl. So which one comes first in alphabetically? B comes first, then 1. So we have to write 1 2 3 4 5 6. So after 1 we have to give the lowest number to the second substituent. So 1-butyl 3-methyl benzene. What about the second one? This is your methyl substituent, this is your ethyl. So E comes first, then M, then we have to start counting from here. 1 2 3 4 5 6. 1-ethyl 3-methyl benzene. So this is how you normally write a substituted benzene if you have more than one substituent. So yeah, I think that should be it from this introductory organic chemistry chapter. Make sure you practice the naming of all the kind of topic that we used in this PowerPoint from your textbook, and then try to do some more example from the textbook, right? And then I'll see you in the next video. Bye.